is Jack Jackson. In this video, we're going to be looking at the derivative rule for the derivative of a linear function. So I'm using my Calculus Collected Resources GeoGebra book here, and I'm going to go to number 4, derivative formulas. Go to derivative of a linear function. And so if we look at a linear function here, there's an example. I can change this here by changing the value of m, either by the slider here or by typing in a number. And I can change that value of b here. And this is illustrating this in the slope-intercept or slope-y-intercept form. 0b is the y-intercept. Right now that's 0, 1. And the slope in this case is 2.5. So it says every time we go the right one, we go up 2.5. Where? Anywhere on this. So a linear function has a constant slope, a constant rate of change. Well, think about what the derivative function is going to have to look like. If we take any 2 points on this graph, any two, and do the line between them, we get the original line back. So that's called the secant line when we talk about the graph, the line between 2 points on the graph. But the secant line is the same as the original line, and therefore it has the same slope. And so actually it turns out the limit of those as the distance between those 2 points goes to 0 becomes the slope of the tangent line. Well, the tangent line is the same line as the line here. So the line, its tangent lines, its secant lines, they're all the same line, and they all have the slope the same as this coefficient right here, which is 2.5. So the derivative is just going to be a constant function, 2.5, which of course has a graph of a horizontal line. So the derivative of mx plus b is just m. The b part here, notice, does not change the slope. If I do this, we can think of this as doing a vertical shift to that blue line, and it doesn't change the slope there. The proof is pretty straightforward. There it is there. I'm going to show you a little bit bigger version of that here from my notes here. So let's make that a little bit bigger. And here's the proof, algebraically. We start with the definition of the derivative. F prime of x equals the limit as h goes to 0 of f of x plus h minus f of x over h. That's the definition of the derivative. And for our formula, f of x equals mx plus b, where m and b are constants. So f of x is mx plus b. Put that in parentheses. Put in parentheses here the same formula with x being replaced by x plus h. That's what f of x plus h means. Now I'm going to get rid of this first set of parentheses around here. And I'm going to distribute the m's. This gives mx plus mh. Then I got plus b. And here I'm going to distribute the negative 1. So this becomes minus mx minus b. Now if you notice the plus b and the minus b here, they cancel. The mx and the minus mx here also cancels out. So the numerator boils down to just being m times h. Now notice all the way from the very beginning, the first, second, third, fourth step, any of these, if we plug in h equals 0, we get 0 divided by 0. This always happens when we're doing a derivative formula. But at this point, h is not actually 0, it's only approaching 0. So we can cancel these h's out, and we see that this is equivalent to just the constant m, and if you take the limit of that as h goes to 0, you get m. So the derivative is a constant function, m. So applying that to a real example here, algebraically, the derivative of 5x plus 7 is 5. Pretty easy to do, right? Okay, let's try another one. You do this one. The derivative of 8x minus 3 is, well, hopefully you said 8. Pretty easy to do. Here's a contextual example. We discover that over a certain period of time, a company's sales of pens is modeled well by the linear function q of t equals 450t plus 12,589, where q is the number of cases of pens and t is the time in years. What is q prime of t? Interpret your answer in the context of the problem. Okay, well, Q prime of t is just the derivative here, which we know is, hopefully figured out, is 450. That's a constant. Okay, and this says that for this period of time that the model applies, the sales of pens are increasing by 450 cases per year every year. And so there's a good contextual example of that. Okay, so that is a linear function rule. Again, another one that's very easy to see why it means it algebraically, and also why it means why it works geometrically, and it's super easy to apply.